Hi, everyone. I'm Molly Simon, an assistant professor at Arizona State University and the education lead for the Zuniverse. Today, I'm going to give a talk titled Why Citizen Science? Unlocking the Potential of People-Powered Research. So first, I want to briefly go over what citizen science is and what the Zuniverse is. With the expansion of big data, many research teams across a variety of disciplines are left with more data than they know what to do with. Machines can help with algorithms and machine learning and artificial intelligence, which can help reduce the scientist's load, but machines require training and are not as good at tasks that they are not programmed to perform. So one of the great things about citizen science or people-powered research is that scientists in fields from astronomy to zoology can post their collections of hundreds or thousands or hundreds of thousands of images. And depending on the platform, anyone, regardless of their background, age, or location in the world, can answer a series of short questions and help the research team with the first step of their data analysis process. So it's amazingly effective. We have many people looking at each image, and researchers can synthesize and study their data much faster than if they were working by themselves or just in their small research teams. So the Zuniverse in particular works in a specific way. We have volunteers all over the world who classify independently. So all of the crowdsourcing is done independently and not in small groups. There are between 3 and 80 classifications per subject. So a subject could be an image, a text file, a video file, a sound bite, and between 3 and 80 volunteers look at each subject. The responses are ultimately aggregated for consensus, and then the raw and consensus data are made available to researchers. And then when the research teams have finished their project that involves their data and ultimately usually have published their results, these consensus data are made public. And then volunteers, while they're classifying on the projects, can interact with the research teams on each project's talk board, which I'll discuss a little bit later. Zuniverse began with a single project called Galaxy Zoo, which was launched in July of 2007. So the goal for this project was to process over 1 million images of galaxies from the Sloan Digital Sky Survey and to bin them into 2 types, spiral and elliptical. The grad student initially tasked with this project calculated that it would have taken him at least 3 years of working 24 hours a day, 7 days a week to get through all 1 million galaxies. And I know that grad students have a reputation for working very hard, but even that seemed a little bit excessive. So he created an online interface to crowdsource the data to the public. The several thousand volunteers who participated not only completed this task in a matter of months, but each of the 1 million images were classified an average of 38 times as opposed to once, which rendered excellent quality data for each of these images. And there was about a 97% agreement between volunteers and experts when comparing a sub-sample of these galaxies that the research team had classified. The success of Galaxy Zoo led to the foundation of the Zuniverse platform as we know it. So since the inception of Galaxy Zoo, Zuniverse has evolved into the world's largest online platform for citizen science. We have had over 350 projects that we've hosted on the Zuniverse site across a variety of disciplines, from astronomy to zoology, ecology, biomedical sciences, geophysics, and we're even in the digital humanities space now. So we have slightly over 2 million registered active volunteers worldwide that contribute to classifying on these projects. And I know this is an astronomy-based talk, and Zuniverse is particularly famous for Galaxy Zoo, which is the largest project on our platform, but I can imagine that many of the listeners have a variety of scientific interests that are beyond astronomy. So I just want to take a little bit of time to highlight the diversity of projects that you can contribute to as a Zuniverse volunteer. So many of our projects, regardless of discipline, have this type of format where the research team has an image, video file, or audio clip, and the research team needs the public's help classifying, tagging, marking, or annotating these subjects in some way. So this project, Snapshot Serengeti, is another good project to talk about how Zuniverse gets its data reliably. So for this project, 25 people classify on each subject, which is an image, and the research team uploads a subset of expert classified images to compare how well the users classify the animals when compared to the experts. On Snapshot Serengeti, there's roughly a 97% agreement between the experts and the volunteers, and oftentimes in that 3%, the experts don't even agree with each other. So we are getting accurate and reliable results from our volunteers. Projects on the platform use the same method of consensus, or multiple people looking at each file regardless of the type of task that that particular project requires. So in this example, we're looking at a marking task where volunteers are looking for star forming regions within our Milky Way galaxy. And what happens on the back end of all of this is that the research team is able to use aggregation routines that the Zuniverse developers have created to take all of the drawings and find ultimately the consensus result. Through the Zuniverse platform, we've demonstrated that consensus and people-powered research is really a powerful tool for scientific discovery. So discoveries directly involving citizen scientists and the Zuniverse have led to over 200 peer-reviewed publications, with thousands more that use our public data from these projects that come from the platform. Citizen scientists that have a particular interest or expertise around a certain project can reach out to the project leads and take a more active role in data analysis. And many of these citizen scientists have been added as co-authors to a variety of these scientific publications. I want to also highlight some of the more exciting and recent discoveries made by citizen scientists in astronomy, featuring two of our most popular astronomy projects, Exoplanet Explorers and Planet Hunters. So this project, Exoplanet Explorers, uses K2, which was a space-based telescope derived from the Kepler mission. And citizen scientists looked at transit light curves, or plots of periodic dips in a star's brightness over time to identify potential planetary candidates. Because when a planet orbits around a star, it will lead to periodic, very small dips in that star's brightness as the planet passes directly in front of it. So, and in this data set alone, citizen scientists discovered 28 new planetary candidates. The transit signals of all of these planets were weak, and they were missed by the automated searches that the Kepler pipeline had in place, because there were a variety of constraints that the computer was programmed to look for that people are not necessarily programmed to look for. So our citizen scientists were able to discover planets that the pipeline had glossed over. Planet Hunters is a similar project that's currently in its 11th year and has now moved on to looking at the first set of transit light curves from TESS, which is the Transiting Exoplanet Survey Satellite. This was launched into space in 2018 after Kepler's tenure was complete. And the task in this project is different because it's the citizen scientist's job to identify the dips in the transit light curves in the first place, rather than vetting previously identified transits like the Exoplanet Explorers project did. So as you can see in this GIF, we're looking at a transit light curve, and the job of the citizen scientist is to draw yellow boxes around where they see the dips. Citizen scientists are particularly good at identifying planets on slightly longer orbital periods where just one transit is recorded. So when the planet is a little further away from the star. These automated pipelines, like the one I mentioned for K2, are trained to only consider a transit to be legitimate if it can identify 2 or more dips. So this biases the pipeline towards planets on shorter orbital periods that are passing in front of the host star more frequently. So this is why the human eye is so valuable when catching things that computers can miss. While these types of discoveries are amazingly beneficial to their respective fields, what Zuniverse is particularly known for are some of the discoveries that happen by accident, or these serendipitous discoveries. One of the greatest features of the Zuniverse platform that I alluded to earlier are these talk boards that each project has. So these talk boards allow volunteers to communicate directly with each other and the research team, kind of like a chat room, if they have a particular question or if they have found something unique. So like I mentioned earlier, humans have this innate ability to recognize patterns. We can look at a data set and complete a specific task, but we can also look at something and say, you know, that's really strange, that's really unique. I wasn't trained to classify something that looks like that. So what is it? And this brings me to one of the most well-known accidental discoveries from Zuniverse projects, the green pea galaxies. So volunteers classifying on the first iteration of Galaxy Zoo started a discussion thread called Give Peas a Chance, with a small collection of green pea-looking subjects from the project, like the ones pictured here. Soon, a lot of other volunteers had contributed to that discussion thread and had identified over 100 of these green pea-looking objects. So this finally caused the research team to investigate, and they ultimately found that these green peas are very small, compact galaxies, much, much smaller than our Milky Way galaxy, with low metallicities, and they're among the most active star-forming galaxies in our local universe. Since 2007, there have been over 50 of our 200 peer-reviewed publications that have utilized just Galaxy Zoo data. So this is a very popular project, and it's also constantly generating new discoveries. Another famous discovery was hanis warwork, which came about when citizen scientist and Dutch school teacher Hanny van Arkel started noticing these blue blobs near galaxies in the Galaxy Zoo data. So she posted her findings on the talk site, and the research team was able to discover a new class of object called a quasar ionization echo, which unfortunately I cannot tell you about in too much detail because I'm not a cosmologist. But these quasar ionization echoes are basically remnants of a small galaxy that underwent some sort of radiation due to interaction with a quasar. So they named these objects hanis warwork, which means object in Dutch, after Hanny van Arkel, the citizen scientist who first noticed them in the Galaxy Zoo images. You also may have seen the headlines, Citizen Scientists Discover Aliens. So this is the story of the WTF, or What the Flux star, a Kepler object with a very weird transit light curve. The leading idea now is that the system has a comet that is breaking apart as it orbits around the star, but what originally was pitched by the citizen scientists is that they had just discovered aliens. Unfortunately, we have not confirmed that these are aliens, but cometary debris seems a little bit more likely. So Daryl LaCourse, a volunteer, was classifying in Planet Hunters when he came across this light curve, and what happened next is what made this discovery possible. So he brought this object to talk and said, "This is very strange. I think it's worth a closer look," and it intrigued him. And so this is one of my favorite posts in all of talk. He shared his ideas, and I really like the last line below the figure, which is, "This is a good opportunity to rampantly speculate and paint." So the key here is that he had a supportive community culture, so he felt like he could publicly speculate, make mistakes, and be wrong. But this ultimately moved the conversation to a collaboration between the volunteers and the research team via these talk boards. So there are a few different groups of social science or crowdsourcing researchers who are looking to study Zuniverse as a system. So this study by a group of economists looked at the relationship between engagement with your volunteers and impact of your project on your particular research field. So each axis is an aggregation across a lot of metrics like number of posts in talk, number of blog posts, and number of articles, citation to these articles, etc. So the main thing to note is that there are no projects with high public engagement and low impact on their science. So some teams naturally have leaders who know how to do this well. They have researchers who engage with their volunteers on talk. Most of these leaders are early career scientists, but some of our research teams require coaching and guidance. So this is an area where we would like to expand because we definitely want to increase our user engagement, which leads to more findings. So ultimately, we want to provide training to our research teams on how to engage and how to create a supportive culture between them and their volunteers. So some of the next steps that we get asked a lot when we give talks about the Zuniverse is, why don't we just have machines do a bulk of these classifications that we're having humans do? So we know that human citizen scientists are awesome for all of the reasons that I've discussed earlier, but it's important not to discount machines when it comes to looking at giant data sets. Like I said, humans are very good at recognizing patterns and making serendipitous discoveries, and catching things that machines have not been trained to look for. So what we're really doing now at Zuniverse is starting to integrate the power of machine learning combined with the human eye to speed up our classification process on many of these projects. This is in perfect timing because SLST, aka the Vera Rubin Observatory in Chile, is going to generate loads of new astronomical data. This ground-based observatory will be collecting 20 terabytes of data per night, 60 petabytes in 10 years, and will be serving over 10 billion galaxies. If you remember from the Galaxy Zoo discussion earlier, it was going to take one grad student over 3 years to look at 1 million galaxies, and now we will have surveyed 10 billion galaxies with Vera Rubin. As a result, there will be a roughly 25-fold increase in the amount of data we are getting back today, compared to what we are getting back today. So in 2022, we are just going to be inundated with astronomical data. So that's why it's very important to really perfect how we can combine machines and humans. And one way we're practicing this out is with the enhanced version of Galaxy Zoo. So the machine classifies images and selects a set that would be the most useful for improvement, and volunteers classify the selected images, which feeds the machine new information simultaneously. So all the images are classified by about greater than 3 volunteers, but fewer than the traditional model, which had about 40 volunteers looking at each individual galaxy. And this project is being led by Mike Walmsley, who's a PhD student at University of Oxford. And you can try out and actually work on the Galaxy Zoo enhanced model on galaxyzoo.org. So an example of the efficacy and efficiency of this strategy is work that was done by a researcher named Melanie Beck, and she created a workflow on Galaxy Zoo as part of an experiment not dissimilar to what Mike Walmsley is doing. So she posted a subset of Galaxy Zoo data on the Zuniverse platform, about 200,000 galaxies, and she found that it took volunteers 300 days, so slightly less than a year, about 10 months, to classify all 200,000 galaxies. On the 7th day after her initial release of this data, she ran a machine learning program she wrote to bin galaxies into the same categories that the human volunteers were asked to do. So immediately the machine learning algorithm was able to retire some of the easier galaxies with very identifiable features. And over the next 23 days, while humans were still classifying in tandem and subsequently feeding the machine with new information, the machine learning algorithm retired all 200,000 galaxies. So it was a factor of 10 increase in efficiency when you have the human and the machine working together. So this is great for optimization, but we don't want to go to machine entirely and miss out on these serendipitous discoveries or these more confusing features that humans are better at identifying. So now that we've learned about the potential discoveries and a few of our Zuniverse projects, I just want to highlight how Zuniverse can be used in the formal education environment or the classroom. So Zuniverse has a classroom sister site, classroom.zooniverse.org, where educators can access a variety of curricular materials for all ages on this classroom site. But I want to highlight 2 in particular in this talk. So as part of an NSF IAU's, or Improving Undergrad STEM Education, funded research effort, we have developed 2 lab-like activities that can be used in introductory college science courses, online or in person, on the topics of transiting extrasolar planets and climate change. And both of these lab-type activities incorporate 2 of our Zuniverse projects, Planet Hunters and Floating Forests. So the Planet Hunters project is more in the astronomy planetary science space, but we've also had astronomy instructors pilot our Floating Forests activity because it can definitely serve as a lab in the more earth science or geology space as well, and definitely environmental science. So as part of the exoplanet classroom experience, students will take about 75 to 90 minutes and complete 3 different components that are meant to be used all together, but also can technically be used independently if instructors don't have the full 75 to 90 minutes. So first, students learn about transits, and they practice identifying transits on a curated set of light curves, where they receive feedback after each transit they identify about whether they've identified it correctly. And this is not something that's a typical feature of Zuniverse projects. So it gives students that confidence, even if they've never classified on citizen science projects, or if they don't view themselves as particularly science savvy before they go on and actually contribute to the real data set. So students will make between 25 and 40 classifications on Planet Hunter's tests, and then they participate in a more data-driven exploration that focuses on characterizing the full set of discovered transiting exoplanets on the NASA Exoplanet Archive, and students look at graphs and data representations to answer the question about whether or not our solar system is unique. And I don't even think scientists know the answer to that question. So it just shows students that we have these huge unanswered open-ended questions still in science, and they can use data and data tables and data representations to make evidence-based conclusions when presented with new and complex questions. Our floating forest activity follows a very similar design model. And in this activity, we use kelp biomass data collected by the floating forest team to identify kelp in Landsat satellite images. And this ultimately creates a global kelp distribution map around the world. And this map has many uses, but we explored the biomass data and found that in regions where the ocean had warmed by only about 1 degree Celsius, there were significant and visual decreases in kelp biomass, even during the primary kelp growing season. So we use kelp biomass as a proxy to teach about climate change and how ocean warming has an effect on ocean ecosystems. So students first learn about the highlights of climate change through a lecture tutorial type activity similar to the transit activity, where we emphasize concepts such as greenhouse gases, atmospheric carbon dioxide over time, the carbon cycle, and human impacts on the environment. So students then learn to distinguish kelp from other kelp lookalike features in Landsat images through a floating forest practice module. And then they can compare their answers to floating forest research team members. And then the students actually classify on floating forests. And in the final part of the activity, students use totally unmanipulated kelp biomass data directly from the floating forest team and global temperature data to learn about kelp growth, seasonal cycles, and the effect that ocean warming has on specific kelp populations and warming hotspots. So we are developing 2 additional lab type activities for college students using the Zuniverse projects, Planet 4 and Gravity Spy, except these 2 new activities were also informed by best practices for making curricular materials inclusive and culturally responsive. So the Planet 4 activity predominantly is based around Martian weather and climate and is being pilot tested this semester. And Gravity Spy will be predominantly around the topic of gravitational waves and LIGO and will be ready in the spring. But for a comprehensive list of other Zuniverse-based resources, particularly for online classrooms of all ages, like lesson plans, access to different activity guidebooks, and links to additional classroom materials, you can go to this link to be linked to a blog about all of our citizen science-based online resources. So I invite you all to join in at zuniverse.org. Here is my contact info if you have any questions. And it would not be 2021 if I didn't end the talk by highlighting that we have an app. So feel free to classify on the Zuniverse app in the iOS and Android app stores. And let me know if you have any questions or want to utilize or pilot test any of our introductory college level labs. Thank you so much.